Dr. Francine Berman received her master's and PhD from the University of Washington and came to Purdue University as an assistant professor. She was here for 4 years and then was lured away to San Diego, where she worked for many years and eventually in 2001 became the head of the San Diego Supercomputer Center. In 2009, after leading that group for those 8 years and a number of accomplishments, she then left for Rensselaer Polytechnic Institute, where she was the vice president of research until this last summer, when she stepped down to become chair of the Research Data Alliance. And she will tell us about that during her talk. Fran has cut a wide swath through the field, leading in many, many areas having to do with large-scale computing, with supercomputing, with mentoring of students in the field. She's been recognized as a fellow of the ACM, a fellow of the IEEE. She was the inaugural recipient of the Ken Kennedy Award, which was awarded for the first time in 2009 in memory and honor of Professor Ken Kennedy of Rice. And that award is made to individuals who've had an outstanding contribution to the field of computation and also in community support and mentoring, things that are all very dear to Professor Berman. She also is currently the chair of Section T of the AAAS, the American Academy for the Advancement of Sciences. Section T is the computation part of AAAS, and a whole list of other things. If you want to find out more about her, I'd say talk to her. She's very friendly and approachable, or otherwise there's a lot of things out on the web you can find with your favorite search engine. So with that, it's my honor to introduce Dr. Francine Berman.
All right, you can pin me. I got that.
Okay.
Okay, we're good, thank you. Oops. Well, actually, I'm retiring chair of Section T. Retiring chair of Section T is Vint. And the current chair of Section T is Eric Horvitz from Microsoft. So this is the computer science folks at the AAAS. It is thrilling to be here, and I have to say that when I was here, we were in the 4th floor of the math building. I think we fit on 1 floor, or maybe 2 at the most. It was a wonderful place to be then. It's clearly a wonderful place to be now, and really congratulations to all of you. It's fun for me to come and talk about what's arguably one of the incredibly exciting phenomena that we're all living through, which is digital data in the 21st century. So let's get started. And I wanted to just start with the world we live in. You know, we are in the information age. There's data-enabled everything. Take out your cell phone, you can find the weather, you can make a call, you can play a game, you can figure out whether the restaurant you're at is a good one or not. You can do all kinds of things. And of course, it's had an incredible, the data that we see everywhere has an incredible impact in the world we live in, including our research. So as Farnham said, and as Deborah said this morning, and I'm sure Vint will say this as well, digital research data is really driving our ability to address the many, many complex science and societal challenges. Whether you're worried about climate, global warming, looking at all of the sensor data, whether you're looking at real-time data and having to assess it in terms of figuring out natural disasters, whether you're looking at simulation and modeling and medical data, whether you're using social networking to harness the power of a community. As you'll remember, the Prime Minister of Egypt resigned by Facebook, tried to shut the internet down in an entire country and to see what was going on. This is an amazing thing, and perhaps the most exciting part of it, and I share Farnham's enthusiasm, is what's going on in our kids' bedrooms with our students today, which is a whole generation of people who will take leadership positions in our world in the next decade or two who have never known a world without the internet, never known it. Communication is Facebook, it's tweets, it's Gmail, it's whatever people are using. But this is a technology-savvy world, and it's a technology-savvy generation. And as much as things are transforming now, we can expect them to keep transforming even more aggressively over the next decade or two. So one of the questions for us is, how can we stay on top of it? How can we make the world a better place? And how can we harness all of this? So what I want to talk about today is kind of 4 things. And the first thing is data-driven research, and just give a little bit of taste about how scientists are using data to really make a difference. And I'm sure you can all come up with hundreds of examples of this. The second thing I want to talk about is cyber infrastructure. What are all the underpinnings that make that happen, especially in our research data community? I want to talk about what's arguably the Achilles heel, Achilles leg, perhaps Achilles torso of this all, which is data economics. How do you pay for all of this? And then at the end, I want to talk a little bit about some exciting develops in the global and international space, and talk specifically about the Research Data Alliance and what's happening there. So let's get started. So let's talk about geoscience. And if you live in Southern California, the San Andreas Fault is of much interest to you. And it turns out that the San Andreas Fault, which runs all through California, rumbles on a pretty regular basis. There was a large-scale earthquake, large-scale being 7.1 or so or more, roughly 100 years ago in the San Francisco Bay Area. There was a large-scale earthquake about 150 years ago in Central California. And in Southern California, you're looking at a large-scale earthquake more than 400 years ago. And so, Southern California is more than ready for its large-scale earthquakes. So one of the things that you might worry about if you're in the Southern California area is what will happen during an earthquake? Will our freeways be able to deal with it? Will our structures be able to deal with it? Will our first responders be able to get there in time? So one thing of interest to scientists is, can you model that earthquake? And this is a model that was run a number of years ago, so it's a bit old, but it kind of gives you a flavor of what they're doing. Seismic waves are coming down from an area near Palm Springs. They're passing down through the Los Angeles area and beyond. And if you'll notice, even though those seismic waves have passed, there's still an area of great activity around Los Angeles. What that means is that Los Angeles is still shaking. Why? Well, it turns out that Los Angeles is a sediment-filled basin. And when those seismic waves come down, it's like a bowl full of Jell-O. Everything keeps shaking. And so the idea is, if you live in Los Angeles, what can you do? Now, as we all know, this is a prediction, because that earthquake has not happened. And the prediction comes from, actually, I believe it's Denali. So they took an earthquake model from Alaska. They parameterized it with a lot of sensor data, like Deborah was talking about this morning, from the Los Angeles area. And then they created, as authentic as they could, an analysis for what they thought it would look like. Turns out that this takes terabytes of data to do this. The visualization itself is another kind of simulation. And so this is truly data-driven in terms of data parameterized. Data was used in a kind of complicated choreography in and out of the small supercomputer that this was run on, and then a lot of data was spit out. Well, this is a somewhat old simulation, and if you think about it, you got roughly a kind of neighborhood by neighborhood resolution on this. You didn't have structures on this. And so if you're a geoscientist, what you want to do is really improve that. You want to put structures on it. You want to get a finer house-by-house resolution. And it turns out that from going by terabytes of data, you really go to petabytes of data in terms of the kind of data you're dealing with. This is important. It's important to the geoscientists. They learn a lot about the San Andreas Fault and geoscience. It's important to the building inspectors and the city of Los Angeles, who might want to retrofit bridges and buildings and building codes, et cetera. It's important to the first responder community to know where the pathways are that are most likely for them to take, et cetera. So this is science that has an impact broadly, and it's science that produces a lot of data. Now, it turns out that scientific applications like this are kind of in that upper quadrant. So they require more compute than you have at home on your laptop, and in this case, they require more data than you're typically keeping on your hard drive or your thumb drive or stuff like that. But the fact is there's incredibly important scientific applications all across this spectrum. There's some that you can do on your laptop or your cell phone or whatever you need in a very, very small scale. You don't have to do anything special. There's data that doesn't require special compute, but you might be using data from something like the Protein Data Bank, which does need some special infrastructure. There's data that maybe the data is manageable on your own, but you need a supercomputer, like the Science Gateway, the Cypress Gateway, which Fran mentioned, which is focused on tree of life, phylogeny, and ontology kinds of analysis, uses a supercomputer, keep your own data. So you're seeing a spectrum about it. It's not just about the size of your data, it's about how you use your data, where you store your data, what you want to do with your data, et cetera. Now, it turns out that as we look out into the next decade, this is just the tipping of the iceberg as to where we are now. We are seeing a number of data-driven technologies that are going to really give us even more things to play with. If you're in the supercomputer world and you're thinking about exascale and what that next generation of supercomputers looks like, you're solving power problems, you're solving programming environment problems, you're solving a lot of different problems. Maybe one of the most interesting things for the rest of us is even if you're not doing a large-scale, quantum chromodynamics application or a big astrophysics application on the supercomputer, we're going to see a trickle down. And we're going to see the kinds of enterprise supercomputers and the kind of enterprise computers that we see in a business, in a college campus, et cetera. All of a sudden, we're going to start seeing terascale and petascale. We're going to be able to do that on our computers. We're going to be able to do amazing things on our lower level devices because it's going to be trickling down there too. So if you're thinking about the kind of science we do at our level, things that you don't have to go to Lawrence Livermore National Lab, San Diego Supercomputer Center, or a host of other places, even those are going to become more interesting. As Deborah said, these smart devices are going to make a tremendous difference. We can crowdsource things. We can get new information flowing. If you sort of follow the DARPA red balloon experiment, where you had to kind of find the red balloons, and people did it through social networking, there's tremendous potential in these small-scale devices, especially coupled with other kinds of devices. If you're following the computer that won Jeopardy, which was an outstanding both stunt, but also really helped the community learn a lot about artificial intelligence and about the kinds of services and augmentation computers can bring to life. You look at augmentation, you look at informatics, you look at analytics. They're really tremendously changing, not just the way we do our work in academia, but the way we do our work across the spectrum. You've got computer augmentation for law, for medicine, for all kinds of things. That's not all. It turns out that data-driven innovation is also transforming our academic institutions and communities. As Fran mentioned, MOOCs are a big deal. And it's a big deal because, as Spaff and I were talking about earlier today, the business model behind universities is really challenged right now. And it's not likely to get any better. But a lot of the things that we're doing right now, the kind of collaborations that you see between universities, think about the airlines before they started coupling together. And now you have groups of airlines that actually share resources. Universities are beginning to do that. You think about MOOCs, and they're actually helping us transform to T-shaped universities, where you can go out and get outstanding classes that you have your students take and do the deep dive, labor-intensive, project-intensive stuff at the residential university. So it's really transforming the way we do things. A lot of data when you have 20,000 students or 100,000 students. You think about the democratization of the way we publish. You're starting to see Public Library of Science. You're starting to see data collections coupled with publications. All of that is really transforming the way we think about data. So it's a really exciting world to be in. Tremendous number of challenges in getting the infrastructure right, getting the economics right, getting the social activities right, getting the regulation and policy right, but it's a tremendously exciting world to live in right now. So what I thought I would do is talk a little bit about what is some of that infrastructure that you need. You know, what are the things that underlie your ability to get the data that you want today, tomorrow, and at any point. And we can start with a representation, lots of representations about the data life cycle. But this is as good as any. So the first thing that you want to do is you want to create your data. It might be created from an experiment that you do, might be created from an instrument, might be created from a sensor, might be created from a camera, an image, an X-ray machine, whatever. But at some point you get a lot of data and then you want to do things to your data. You want to organize it, you might want to create a different time series about it, you might want to clean it or filter and throw out bad data if you think there's bad data in there, etc. Then for the scientific community, it's tremendously important that we can use that data, that our colleagues can use that data, that we can reuse that data, etc. You want to analyze it, you want to mine it, you want to model it, you might want to create a derived data set from it, you might want to use it as input to other kinds of devices, etc. Then you want to get the message out. You want to publish it in a paper, perhaps it has an attached data set, you want to create a portal, you want to send it to someone, you want to do all kinds of things. And then at some point you have to be thinking about the life cycle itself. And perhaps you're storing it and ignoring it. You know, too bad if my hard drive crashes, that's the way it went. Wasn't important anyway. Maybe you want to store it and preserve it. Well, I'm going to preserve it. I'm going to make sure I have another copy. If you've looked at the Byzantine generals problem, you know, you're safe if you have at least 3 copies, or in some conditions, at least 7 copies of your data. So you want to make sure people in other kinds of geographical locations have it. So, you know, you might have a tornado and somebody else might have a fire. Less likely that you have it at the same time. So there's kinds of things you want to do to preserve the different copies of your data. You might want to destroy your data. So whatever you want to do with it, you have to be thinking throughout the data life cycle about what's important. Now, it turns out that what you want is the kind of underpinnings that help you do those things with it. So whether your data came from instruments or sensor nets or computers, or whether you're simulating with it or visualizing it, etc., you might want to use particular services with it. There are statistical packages you might want to use to manage your data. There are domain-specific tools. If you're an astronomer, you might want to mosaic it, for example. You might want to de-identify it or analyze it or visualize it. So, and whether these things are in a cloud, whether they're in a specific center, whether they're at your site or not at your site, what you want is to be able to access it, to share it, to store it, to manage it, to preserve it, to use and reuse, etc., depending on what you're doing. So there's a lot of stuff that you want to do with your data. Now, it turns out that in addition to stuff that you want to do with your data, we're now seeing the agencies really start thinking about what they want you to do with your data. And so now if you go to NSF or NIH, and most of the agencies have some version of this, there's a requirement for a data management plan. How are you going to manage your data if you believe that it's valuable? Now you can say it's not valuable. The first version of this talk I just threw out. You know, it's not valuable to me, it's certainly not valuable to you or anyone else. So the idea is that, you know, still, and we'll talk about this in a little bit, the research community is self-selecting about which data might be valuable to the researchers and the colleagues. But if it's valuable, you need a plan. And moreover, and Fran mentioned this as well, we saw, and these things are thrilling, but they're still unfunded mandates. There's an expectation that we have public access to the results of federally funded research. And you see, you know, these great things, we paid for the research, so let's see it. Well, we may have paid for the research, but we didn't necessarily pay for the infrastructure that will help serve us up. So the economics of this comes back again and again as a really important thing for us to be thinking about. And I think, by the way, that the public access of federally funded research is tremendously important. And I think this is a very important time for us to take advantage of being able to think through the cyber infrastructure requirements for these research data collections. Now, as you think through the cyber infrastructure requirements, let me give you a sense about what those are. So if you want to keep a data collection, you have a number of costs, and this is our experience at San Diego Supercomputer Center. You have to worry about maintenance and upkeep of hardware and software. You have to talk about various tools and packages. You have to pay for power and cooling. If you have a large-scale data center, Vint can probably tell you all about that. It's tremendously expensive to do that. You have to worry about space and networking. You have to have a UPS system that might make sure that your data is okay if the power goes out. Very important expense in people. You want professionals to be working on the systems. You want data scientists. You want people helping with curation and metadata and all of that. Training and documentation, costs of compliance. Today there's a great deal of compliance. If you look at your average university administration, they are required to be keeping all kinds of paperwork about our grants. So, and that costs universities. They have a data bill as part of sort of their regular set of bills. One of the experiments we did when I was at SDSC was really fun and thrilling and educational, which is that we started something called Data Central, and we said to the community, we will store your data at SDSC. And we'll provide different services, we'll provide different ways of managing it, we'll do it for free, which was challenging. But we said we would do that. And this was our experience, is that over that time, and we stored several different copies of the data. Over that time, there was more and more of a demand, and for us, it means that your storage has to, of course, stay ahead of the game. So that the step function up there, the red step function, has to do with sort of us saying, time to buy more storage so we could keep this going. And then the blue line is the data collections we had. We had over 100 data collections. They varied from art images to astrophysics data to chemistry data to all kinds of things. And it was a tremendously interesting time to sort of experiment with what that's like for an academic institution. This is, remember, academic sector, to be able to kind of integrate that as part of its activities. First of all, one thing to know is that as you get more extreme, the cost in your data, the current buzzword du jour, which is big data. But the fact is that data can become more extreme in lots of different ways. It can become more extreme because it needs to be long-lived, 10 years, 50 years, 100 years. It can be more extreme because it needs to be coupled with services, and so that adds various costs. It could be more extreme because the access has to be special. Either maybe not very many people could see the data. Maybe you want the whole world to see the data. We supported the Protein Data Bank. That was open 24/7 globally. When we were not the only place that did that. But it put real expectations on the kind of networking infrastructure that we had at SDSC. It may be that more management and stewardship is required of your data. So really, as locally manageable data is, I have a copy of the data on my hard drive, I'm good to go. But really, as you move out and kind of have more and more expectations of this data, you incur greater costs. Now, it turns out that when you ask the question of who pays the research data bill, you see something that's akin to what we think of in the supercomputing world as the Branscombe pyramid, which I think of as the data pyramid. And the idea is that there's a great deal of data that's of individual value to me. There's a great deal of data that's of value to a community, and there's a great deal of data that's valuable to society. And we have different ways of dealing with all of this. So when I start thinking about data of individual value, that's data that might be a family picture. This is my actual family. It might be your tax data. It might be data. This is a baby picture of Barack Obama. You can imagine that once Barack Obama is president, he moves to the societal value space. So you see data moving up and down the data pyramid. And we have all different ways of dealing with this. I might put it in Dropbox for my colleagues. I might keep it on my hard drive. I might actually think about having some sort of service for this, et cetera. But typically us and it's between us and the private sector to kind of retain that. When you're thinking about community value, you're thinking about things like the Protein Data Bank, the National Virtual Observatory, the panel study of income dynamics. This is a 40-year or 40-plus year longitudinal study of economics and families. These things are typically hosted at various kinds of repositories. Might be your university library, here's the UCSD library, might be the Inter-University Consortium for Political and Social Research up in the University of Michigan, might be at the PDB, NSF might have some of it, et cetera. And then you look at things of societal value, and you're looking at various resolution photos of moon data, Barack Obama's BlackBerry data, census data, and now he has moved from individual value up to societal value. And the other picture I'm showing is actually a Library of Congress image that they keep, a very interesting image of Russia from the 1900s. They actually keep it 3 different files because this was actually how it was taken with this device that had a red filter, a green filter, and a blue filter. And through the magic of computers, you can actually see them together. So typically you see kind of public sector or sometimes private foundation and academic sector kind of business models. What you see is that as you move up the data pyramid, you see greater public value, greater needs for infrastructure, greater access and preservation requirements, and you see a variety of different models. So typically, the federal government and societally, we've almost figured out really how to support publicly funded data at the societal level. Individually, there's a thriving activity with yourself and your private sector colleagues. But in the middle, this is where we're kind of all over the place. When we look at data of community value, and that's typically the kind of public access data that we're talking about with the OSTP memorandum, we're looking at data that's hosted, it's perhaps individually, perhaps publicly, perhaps privately, that it's funded, perhaps individually, perhaps institutionally, publicly and privately funded. And we don't really have our act together about a good, consistent framework for doing that. And that's our challenge right now. And it's an important and special challenge. It's a thrilling challenge because we're at that place that we can start thinking about it seriously as a country. But it's a challenge nonetheless. So let's think about that middle of the data pyramid. And let's ask the question, how can we better support research data of community value? And it turns out that it's as complicated and simple as the stakeholder problem. So the greater the alignment between the key stakeholder groups associated with that data, the more likely you're going to get a good, sustainable business model. So who are the stakeholders? The stakeholders are, people who select the data, and typically for research data, that's often the researchers themselves. People who have rights to the asset. So if you have a proposal, it's through Purdue University, you and Purdue have some arrangement, but Purdue really gets the money for that. National Science Foundation has some, or NIH, or any of the other agency, have some call to that, et cetera. So rights in the digital age, kind of challenging. There are stakeholders who benefit from use of the preserved asset. Often for the research community, that's everybody. If you can make it available to the general public, obviously if there's HIPAA compliance requirements or something like that, you can't, but typically many people want to see it. There are stakeholders who preserve the asset. That might be a third party. Maybe you preserve it in a commercial enterprise, maybe you preserve it in a private repository or at your university library, et cetera. And then there's stakeholders who pay. And perhaps NSF is paying. But what happens if you've said, my data is really valuable, it's going to be valuable for the next 10 years, and your grant only lasts 3 years? So what happens for that next 7 years? And that's what we're grappling with right now. Now, this was looked at in depth. I had the great good fortune of co-chairing with an economist, Brian Lavoie, and a set of tremendously knowledgeable people, an actual deep dive report into the economics of data, including research data, and really starting to look at what kinds of things. So if you're interested, this is the read more about it part. Go to brtf.sdsc.edu, and there's more information about that there. Okay, so this is in the academic world, and we are challenged. But the fact is, we pay for data all the time in the real world. And we do a whole bunch of things. We provide donations. I sent in my donation to Wikipedia just recently. We do federal grants. We might pay for service. When I go to my Google browser, there are advertisements, and that helps pay for things. I wake up, I look on my iPhone, and I have a subscription, digital subscription to the New York Times. So they started asking me paying for data. What am I paying for? Well, think about your average New York Times article. I'm looking at text, I'm looking at audio, I'm looking at video. There might be an associated data collection or a link. This is the publication of the future. This is, what we're doing in the real world, and it's what our scholarly publications are more and more going to look like. And of course, we're doing crowdsourcing. So this is a talented choreographer who actually got people to donate money to pay her dancers. And so this is Kickstarter. You can donate to kind of arts and other kinds of projects all the time. And in fact, this is sort of philanthropy for the rest of us. So you can actually crowdsource small amounts of money to help. And this is one way we're paying for data as well. Now, it turns out when you start looking at economic sustainability, it's easy to point your finger at some sector and say, well, they're going to do it. NSF's going to do it all. Federal sector is going to do it all. Private sector is going to do it all. Your library is going to do it all. And the fact is that no one sector, is going to do it all. The key is really to have a broad set of solutions and a broad set of partnerships, because the private sector has to worry about staying in business. That's what it means to be in the private sector. And they have to be very strategic about what they do. The academic sector, there's a lot of demands on any university budget, any university library budget or other kind of budget, as you know. And the federal government does not have the funding to sort of provide all of the infrastructure for all of the valued research data out there. So the fact is we have to come up with a more broad-based set of solutions. So I have 4 modest proposals in this part of the talk about things that we can do and things that I think are worthy to sort of work on. And they have to do with all of the sectors. So the first is, let's facilitate the private sector's stewardship of public access research data. Now, if you think about it, private sector companies provide philanthropy all the time. You go to the ballet, sponsored by, and you can say, who might have sponsored a particular ballet program. West Virginia is providing tax credits to sponsor performing arts. This is when IBM was doing World Community Grid, and they were developing a philanthropic activity to look at social impact kinds of things. So if we give the private sector a little on-ramp to that, pennies on the dollar, tax credits, other kinds of things, we could see possibly, interested in hearing Vince's ideas about this at some point, more engagement through the private sector for public access research data, which I think is tremendously important for us all. Not the only solution. The next thing I think we need to do is we need to help the academic sector. And if you think about it, your standard university library is really struggling to reinvent itself in the 21st century, when the average student who comes to your university, if they want information, they're sitting in a Starbucks and looking it up using Google and Wikipedia. So if you think about what libraries are doing in the digital age, they have a tremendously important role to play. They can help curate our data, they can help manage our data, they understand all about the sort of legal and rights issues with respect to our data. What they need is help. And what they need is to build out capacity and data science professionals to be able to do that. Imagine there was some on-ramp programs, just like there were on-ramps to creating supercomputers throughout the United States. Imagine there was an on-ramp program for libraries to be able to start catching some of that data for our researchers and to be able to sort of create a sustainable solution to the data bill in the universities. That would be something that would be worthwhile to work on. When you think about the public sector ought to be keeping some of our data, but the challenge for them is they can't keep it all. So the question is, which research data should they collect? How long should we keep it? How should that funding be decided between something that the public sector builds within itself and something it outsources? Who should host that? And so those kinds of questions are really important questions to deal with. And in fact, the question between how much money for research and how much money for infrastructure is a good question to be clarified. So those kinds of issues are really important. And then last but not least, let's do what works in the real world. So imagine that I have the National Virtual Observatory, and I want to be getting data from all the different sky surveys on that and the protein data bank. You know, so I go to my iTunes, and honestly, if I want Lady Gaga or, you know, Beyonce or, you know, anybody else, you know, there's a, you know, it says pay your $1.29 or pay your 99 cents, et cetera. Imagine I went to the National Virtual Observatory and there was a low barrier for access cost for me to get data from the Sloan Digital Sky Survey or something else. Imagine if that were true. Imagine I went to the Protein Data Bank and instead of just seeing that, I saw some annoying advertisement that helped the Protein Data Bank actually be able to support itself. These things work in the real world all the time. There's no reason that they can't work in the academic world for us to support these things that have tremendous public value. Okay, so let me just finish by sort of talking a little bit about the fact that these are not US problems only. So if you think about what's happening all over the world, we may have our own special issues about economics based on the laws in this country, but all of these data issues, cyber infrastructure, economics, sharing of data, public access of data, are really important all over the world. They're important in India, they're important in France. The European Union has a vice president in charge of digital strategy. In Australia, they have the Australian National Data Service. South Africa has telescopes. There's all kinds of things that generate data, and there's a real interest in data. So in some sense, it takes a village. And I wanted to talk a little bit about an emerging community effort to build coordinated global data infrastructure, tremendously important. And for the Research Data Alliance, we're sort of starting with what's pretty clearly low-hanging fruit, which is data sharing and exchange. All over the world, if you want to solve hard problems, you want sort of the barriers that come up not to be barriers, national barriers between scientists or disciplinary barriers, et cetera. It's not just your data, it's other people's data. And if you think about it, there's this recognition all over the place. The Alzheimer's community has done something really exciting, which is, if you think about it, if you're in the life sciences, your data is your competitive advantage. That's where you get your publications, you want to keep it there, HIPAA requirements, et cetera. It's hard to share your data. However, the Alzheimer's community has actually gotten together, and a number of different players have created an interoperability framework and a mutual data collection where they can share and create a much larger community Alzheimer's data collection and make it available to the public. Now, what did that mean? That means that instead of looking at, you know, hundreds or thousands or tens of thousands, whatever your patient population is, you can go up an order of magnitude. All the trends from noise, fine resolution analyses you want to do, you can do it on a much bigger data set. Very important. And in fact, the Alzheimer's community has gotten many more new results because they were willing to, you know, create that interoperability framework, create kind of a common metadata, and create policy that allow them to share. The autism community has done that. And if you think about it, it sort of goes on the heels of what we did with the Protein Data Bank. When we created policy, NIH created policy over 40 years ago, which said if you're doing a particular kind of federally funded research, you want to deposit your protein structures into the protein data bank. And because of that, we have this tremendous resource for the community. So data sharing is really important, and it's important to people all over the world. Now, if you go back to the data lifecycle and you say, what are those pieces of infrastructure that really drive data sharing and exchange throughout the data lifecycle, there's a whole bunch of different things. Some of them are policy that you might want to adopt, like the NIH did. Some of them are common metadata standards, so communities can share their data. Might be work on digital object identifiers, access and distribution policies, et cetera. All of these things are pieces of infrastructure you create, you can adopt, and you can use to help researchers move forward. That's the idea behind the Research Data Alliance. So the Research Data Alliance is an international new community organization, and it was formed just this year to accelerate global data sharing and exchange. So the idea is, let me give you an example from our community. Many of you will not remember this, but a long time ago, there was something called the MPI, Message Passing Interface Forum. And Jack Dungara and a number of people got together. They spent 9 months at this. Before that, there were a whole bunch of different communication protocols. If you were a vendor and wanted to create a compiler that would support most applications, if you wanted to write an application with communication, you didn't have a really consistent set of communication protocols. The MPI folks got together. In 9 months, they created a reference implementation. People, the vendors sort of picked it up, the application people picked it up, made tremendous advances to the community. Was it perfect? No. Did they have to tune it over time? Yes. Is it the only kind of communication protocols people will ever use anytime? No. However, it made tremendous difference in terms of, how the community went forward. These are the kind of activities that the Research Data Alliance will do. Short-term pieces of infrastructure that people need to adopt that will move the community forward. Could be any one of a variety of things. Could be adopted standards, deployed infrastructure, adopted policy, like the NIH policy, implemented best practice, et cetera. These give you some of the tweets from the event. So let me tell you a little bit about the event. We were in Sweden a few weeks ago. RDA went live, and we had over 200 people attending the launch, representing 31 countries and 5 continents. There were representatives from public and private and academic sectors. Farnham was here representing the US. Joining him as other high-profile speakers were Neelie Kroes, who's Vice President of the European Union Commission. She's in charge of digital data, the Australian ambassador to the EU and NATO, and other kinds of people. And it was thrilling. You had a number of people who were actually going to do the work, a number of people who really care about research data and exchange moving forward. And we got over 6,400 tweets. These are only a few of them. I'm not going to put them all up. Thank you. Yeah, you're welcome. So what's the Research Data Alliance out? And I'll just tell you a couple more things about it, and then we'll close out. First of all, the deliverables must be concrete, specific pieces of infrastructure that are adopted by someone on the team. So you think about the working groups. They're expected to have 12 to 18 months efforts. They're like a tiger team. So you have the beneficiaries of what's going to be adopted, the builders of what's going to be adopted, and the adopters of what's going to be adopted. They all have to be in that activity. We're looking at creating focus pieces of adopted code, policy, infrastructure, standards. They have to be harvestable efforts. You have to be able to create them and adopt them within this time frame. They should have substantial applicability. They don't have to apply to everyone. So it can't be that we have a working group that says, I'm going to build some global infrastructure and someday everybody's going to buy into it. That's a great Esperanto solution. Our guys aren't going to do that. It's like, what can we do today that can really move communities forward? And those are really key efforts. I thought I would give you a sense of some of the groups that are forming. One of the working groups that we have are looking at persistent identifier information types. Why is that important? You may have a number of ways of creating these persistent identifiers. You want to know when they're talking about sensor data, or when they're talking about some other kind of data, you can make them interoperate. So you could share the data collections that they refer to, and you can integrate them in reasonable ways. If you had this solid piece of code, it's going to be adopted at the German Supercomputing Center and other sites. We have a group that's forming a proposal. I love these guys. They're all about wheat. So if you think about it, agricultural productivity, hunger, very important. But it turns out that the wheat community doesn't have interoperability among all the different data collections. They need to be able to answer these kinds of questions. And so what they're doing is they're developing a proposal to make a number of different kind of data collections around wheat interoperate so they can address some of these harder questions. Current status, we've just had the first plenary. The plenaries will be twice a year. The next one will be at the National Academy, September 16th to 18th in Washington, D.C. Mark your calendars. If you are interested in the Research Data Alliance, joining is easy. All you have to say is you believe in openness and good things. And then you can join a working group or an interest group. You can help us form the organization. It's not completely formed yet. If you have an organization which you think would benefit from affiliation, we're looking for affiliation models. So lots of exciting things going on. And I have to tell you personally, it's just been thrilling to really work at this international level for the data community, because the same problems are really pressing and really exciting people the world around. So you know, in closing, let me just bring it back to this notion of data as an ecosystem, because for us, the end result is innovation, data-driven innovation. This is really the hallmark contribution of the 21st century. In order to have innovation, you have to have the right kinds of components: good soil, sun, water. And what are they? That's infrastructure. It's economic support for the infrastructure. It's community effort to do things that you can't do by yourself in your project, at your university, at your enterprise, in your country alone. So we have to gather together to solve some of these problems. You need policy and regulation. You need practice. You need all of the rest of this. And we really have to look at this in a holistic way. It's not enough to just look at the innovation or the infrastructure or the economics of it. We really have to look at it together. So with that, I want to wish you happy 50th anniversary, 50th birthday. Sure, happy to.
We have time for a few questions.
Sure.
I'm interested in the issue of paying for things that are of community value. If you take the more traditional concept of we're going to have a library, people will vote for bond election to pay for the library because they see a building. There's something tangible. Whereas a lot of things you're talking about are not so tangible. How do you motivate people to pay for it? Because ultimately the taxpayers pay for most of this.
Yeah, that's a great question. The question is, how do you motivate it when there's not this sort of tangible physical infrastructure? And so there's been some changes. If you think about it, the Shoah collection, which is a collection of Holocaust survivor testimony, and it was developed, actually, I think by Steven Spielberg after he did Schindler's List, as kind of part of a private foundation, been taken on by USC and a number of other kind of investors. And this is something where people thought things were important. There didn't have to be necessarily a building there. But a lot of times with philanthropy, you give a philanthropy to something soft, a ballet performance or data. So you would imagine your modern university development offers saying, well, you can name a building, you can name a data collection, the Fran Berman data collection on wheat, whatever. And, so you could do things like that. The other thing is, it's been really interesting to me to watch Wikipedia. And, it's sort of like once a year or whenever, however often they do it, they say, this is really important to you. If you're interested, send some money. So we donate to things all the time. There isn't always tangible infrastructure with it. And I think, as we go forward in the digital age, this goes back to one of the original pictures. In a world with people who, never knew a world without the internet, these things take on real value to you, whether or not it's a tangible piece of infrastructure or not. So I think with the right kind of marketing development and mindset, we could really see a lot more sort of philanthropy with respect to digital activities. Almost.
Okay, so the one question I have is stem cell research. So I'm for it, stem cell research.
Stem cell research.
I don't want to donate yet my kids' stems or anything because there is no policy around. I don't know what people will do with my data. They will know a lot about me. So I was wondering what do you think about policies where individuals share their data?
Yeah, I mean, so the question was about stem cell research. The real challenge of trying to figure out in the policy environment around it, what's okay and what's not. And certainly there's great analogies with respect to digital data. There's a huge issue about, who owns what and who has rights to what in the digital world. If Spaff writes a blog and I go flame on that blog, and then you flame on my flame, and then the Internet Archive wants to preserve it. Do we need to give them permission to do that? Who owns this? And the Library of Congress has just actually started gathering, with obviously in affiliation with Twitter, all of these different tweets. So who owns that kind of stuff, and who has rights to it? So I think those are real issues that we're going to have to deal with. The privacy around all of our data, the rights about who can use it, who can preserve it, under what circumstances, et cetera. I think you're right to have this be a concern, but in some sense you can't put the genie back in the bottle. We're just going to have to deal with creating some models for privacy because in some sense that data is out there one way or another. And the more we can create sensible solutions to try to deal with it, maybe not perfect solutions, but sensible solutions through privacy, et cetera, that's fine. I mean, even with public access data, there's issues about, well, what about the tools that generated it or use it, or who owns it, et cetera. And so those are real issues.
So we have to wait for the first court case?
I think there'll be many court cases. Look at what happened with the machine that, with Watson, that won Jeopardy. And now IBM is doing some really interesting things with that. So it's actually using that to help create diagnoses for oncologists. So it's being used for oncology. Well, they've been really careful because you don't want a computer diagnosing your disease. What if the computer gets it wrong? By the way, your doctors get it wrong all the time, but who do you sue for malpractice? Yeah. Do you sue the computer company? Do you sue the software developer? I think the legal rights around these things are really challenging. Oh, good, okay. Yeah, I'm really happy to hear you say that. I've talked with many of your colleagues, and I think IBM is doing a really wonderful job. And by the way, I think this is incredibly important work because if you think about, Farnham was getting to this at the end of his talk, if you think about the augmented professional, so doctors who can have a computer help sift through in an intelligent way, huge amounts of literature to help them, make decisions. Lawyers can do this, architects can do this. I mean, in some sense, any professional can do it. This is the world we're going to. And the kind of way, you never sit at dinner anymore and say, I can't remember the second verse to Stairway at Heaven, anymore. It's like an old song. It's like you pull out your iPhone, there it is. And so this way that this data is really informing our life has really completely changed it. So things like that are just, harbingers of the future. Okay, sorry.
Paying for data. Well, I can see a lot of data sets that I'd be happy to pay
Well, I'm sad to say that not only can I solve all the data problems, but I cannot solve the parochialism problems at universities as well. I do think that, and this gets to the question of, how much of your money, and you worked hard for that money, the hit ratio, as Farnham said, for these grants is not high. And so how much of that should you spend on infrastructure versus salaries and other kinds of things you need, travel to a conference you need to do for your research?
I can put a line item in the budget for this, but how much does it cost me in terms of the producing an audit trail that the government will accept as I'm spending this money correctly?
Well, I believe
Actually spend the dollar that I put in my budget.
I believe you have an opportunity right now. I remember seeing from my Rensselaer email as I read it this week that, and I'm trying to remember who was asking for it, but there's a request for comments, I think it was OSTP, about the burden, the regulatory burden on researchers. And so, in some sense, you may not get your voice heard if you raise it, but you have no other alternative. So, I think we need to be sharing what these burdens are. But, in some sense, we got to come up with ways to solve it, because sort of going back the old way isn't going to do it. Okay.
Last question.
Okay. Janelle.
So you talked about data that is you already have collected. But what about enabling the community to get access to the kinds of data that is currently available to some but not necessarily to others? I'm thinking, for example, about the data that Facebook gets,
Yeah.
or that Google gets through all their searches. Is there any thought about putting together community infrastructure to build applications like a public Google or a public Facebook so that we could start using these services and thereby generating data which is not limited by proprietary?
I can't speak to that, and maybe Vint can, as to whether there's an industry consortium. But I do think that there's a tremendous opportunity for the academic, the public, and the private sector to be working together on this open access, public access data space. Because I think it's, the private sector is really wonderful. They've got the capacity, they've got the expertise. Their notion of scale is completely different from our notion of scale in academia. They're at the millions and billions space. We're, if we're lucky, at the tens, hundreds, thousands, tens thousands space. And so, they know how to do this. And so there's really an opportunity there, coupling with the public sector and the private and the academic sector in a way that makes it advantageous for them to do it. Because they have to do things that are advantageous to them. That's what it means to have a company, is to look at the health and well-being and survival of your company. So if we can make that part of their mainstream set of metrics of success, then everyone wins. And so those solutions, I think, are tremendously important.
So once again, let's